Section: Introduction. We're going to talk about a type of artificial intelligence, AI, known as an agent. An agent is something that can perceive its environment, make decisions, and take actions. Traditional AI agents have been successful in specific areas, but they often struggle to adapt and generalize their skills. However, large language models, LLMs, which were initially created for language tasks, have shown impressive abilities in following instructions, reasoning, planning, and even using tools. This makes LLMs a great base for developing AI agents with a wide range of functions. Recent projects like AutoGPT, GPT Engineer, and Baby Aggie have used LLMs as their main controllers, creating powerful agents that can solve complex real-world problems. But a recent study found that open LLMs like Llama and Vicuña are not as capable as GPT 3.5 and GPT-4 in complex, real-world scenarios, even though they have performed well in traditional language tasks. The gap in performance is slowing down the progress of LLM research and innovation. Most of the existing studies on LLMs as agents have focused on designing prompts or a framework for completing one specific agent task, rather than improving the agent capabilities of the LLMs themselves. Also, many efforts have been made to improve LLMs in specific areas, which has led to a loss of their general abilities and has limited their ability to generalize. To address this, we're introducing a simple and general approach called agent tuning. This approach includes two parts: a lightweight instruct tuning dataset called Agent Instruct and a hybrid instruction tuning strategy that improves the agent's capabilities while maintaining its ability to generalize. Agent Instruct includes 1,866 verified interaction trajectories with high-quality rationale for each decision step from 6 different agent tasks. To improve the agent capabilities of LLMs while maintaining their general abilities, we experimented with a hybrid instruction tuning strategy. This strategy involves mixing Agent Instruct with high-quality and general data at a certain ratio for supervised fine-tuning. We used agent tuning to fine-tune the Open Llama 2 series, which resulted in the AgentLM7B, 13B, and 70B models. Our evaluations showed that Agent LM performed well on both the tasks in Agent Instruct and unseen agent tasks, suggesting strong generalization of agent capabilities. It also made a AgentLM70B comparable to GPT 3.5 on unseen agent tasks without compromising its performance on general language tasks. Our analysis on the ratio of agent data with general data suggests that the general capabilities of LLMs are crucial for the generalization of agent tasks. Training solely on agent data, in fact, leads to a decline in generalization performance. This can be explained by the fact that agent tasks require LLMs to have comprehensive abilities such as planning and reasoning. Our error analysis on Llama 2 and Agent LM shows that agent tuning significantly reduces instances of basic mistakes such as formatting errors, duplicated generation, and refusal to answer. This suggests that the model inherently possesses the capability to tackle agent tasks, and agent tuning indeed enables the LLM's agent abilities rather than causing it to overfit on agent tasks. Agent tuning is the first attempt to instruction tune LLMs using interaction trajectories across multiple agent tasks. Evaluation results indicate that agent tuning enables the agent capabilities of LLMs with robust generalization on unseen agent tasks while remaining good on general language abilities. We have open-sourced the Agent Instruct dataset and Agent LM. In terms of the agent tuning approach, given an agent task, the interaction trajectory of the LLM agent can be recorded as a conversation history. This history includes inputs from the user and responses from the model. Each trajectory has a final reward, reflecting the completion status of the task. To date, there is no end-to-end attempt to improve the general agent abilities of LLMs. Most existing agent studies focused on either prompting one particular LLM or compiling a LLM-based framework for completing an agent task. According to Agent Bench, all open LLMs are far behind commercial ones such as GPT-4 and ChatGPT in terms of acting as agents, though these models, such as Llama 2, have demonstrated strong performance across various benchmarks. The goal of this work is to improve the generalized agent abilities of LLMs while at least maintaining their general LLM capacities. We present agent tuning to achieve this goal, the first step of which is to build the Agent Instruct dataset that is used in the second step to instruction tune the LLMs. We carefully experiment and design these two steps such that the LLMs obtain good performance in unseen, generalized agent task types while remaining good in general LLM tasks. Section Summary. Traditional AI agents have limitations in adaptability and generalization, but large language models, LLMs, have shown promise in instruction following, reasoning, planning, and tool utilization. However, open LLMs like Llama and Vicuña lag behind in agent capabilities compared to GPT 3.5 and GPT-4. To address this, we introduce AgentTuning, a simple and general approach that fine-tunes LLMs using a hybrid instruction tuning strategy and a lightweight instruct tuning dataset called AgentInstruct. AgentTuning enhances LLMs' agent capabilities while preserving their general abilities, resulting in improved performance on agent tasks without compromising their performance on general NLP tasks. Section. Constructing AgentInstruct. We're going to talk about how we built AgentInstruct, a tool designed to improve the ability of language learning models, LLMs, to follow instructions. This is a challenging task because it involves tracking the interactions of an agent as it navigates a complex environment. We're the first to attempt this, and we'll explain the choices we made during the construction process. The process of building AgentInstruct involved three main stages: creating the instructions, interacting with the trajectories, and filtering the trajectories. We automated the entire process using advanced language models, GPT 3.5 and GPT-4, which makes it easy to apply this approach to new agent tasks. We designed AgentInstruct for 6 different tasks: AlphaWorld, WebShop, Mind2Web, Knowledge Graph, Operating System, and Database. These tasks represent a variety of real-world scenarios and are relatively easy to collect instructions for. They are also part of the challenging agent bench tasks, which most open-source models struggle with. If a task already has a training set, like AlphaWorld, WebShop, Mind2Web, and Knowledge Graph, we use that for the next stages of interaction and filtering. For tasks like Operating System and Database, which don't have training sets, we use a method called task derivation and self-instruct to create the necessary instructions. In task derivation, we use similar datasets to construct instructions for tasks that are widely studied. For example, to create instructions for the database task, we used instructions from BERT, a database benchmark that only uses select commands. We used 2 methods to derive tasks. The first involved constructing a trajectory using a question and a reference SQL statement from each BERT subtask. We then asked the database for the output using the reference SQL statement and used this as the agent's answer. We then asked GPT-4 to fill in the agent's thoughts based on this information. This allowed us to generate correct trajectories directly from the BERT dataset. However, this method only allows for 2 interaction turns, so we used another approach to increase diversity by constructing instructions instead of trajectories. We prompted GPT-4 with a question from BERT and collected its interaction trajectory with the database. We then compared the results of the reference SQL statement from BERT with the results from GPT-4 and only kept the trajectories that produced a correct answer. For the operating system task, we used the self-instruct method due to the difficulty of obtaining instructions that involve manipulating the operating system in a terminal. We asked GPT-4 to come up with some tasks related to the operating system, along with explanations, a reference solution, and an evaluation script. We then asked another instance of GPT-4 to complete the task and collected its trajectory. We compared the results of the reference solution with the results from the GPT-4 solver using the evaluation script and only kept the trajectories where the reference solution and the solver solution matched. We used a similar self-instruct approach for the database task, constructing other types of database operations: insert, update, and delete. We were careful to avoid data leakage, which could occur if GPT-4 produced instructions identical to those in the test set, or if test tasks were constructed from the same dataset we derived from. We conducted a systematic analysis and found no evidence of data leakage. Once we had the initial instructions, we used GPT-4 as agents for trajectory interaction. For the Mind2Web task, we partially used ChatGPT due to the large number of instructions and our budget constraints. We used a one-shot evaluation approach because of the strict requirements for the output format in agent tasks. For each task, we provided a complete interaction process from the training set. The interaction process had two main parts. First, we gave the model a task description and a successful one-shot example. Then, the actual interaction began. We provided the model with the current instruction and necessary information. Based on this and previous feedback, the model formed a thought and took an action. The environment then provided feedback, including possible changes or new information. This cycle continued until the model either achieved its goal or reached its token limit. If the model repeated the same output 3 times consecutively, we considered it a failure. If the model's output format was wrong, we used the blue metric to compare it to all possible action choices and picked the closest match as the model's action for that step. Section Summary. We introduce AgentInstruct, an automated approach for constructing language instructions to improve the generalized agent abilities of pre-trained language models, LLMs. AgentInstruct consists of 3 stages: instruction construction, trajectory interaction, and trajectory filtering. We construct instructions for 6 agent tasks, leveraging task derivation and self-instruct methods, and use GPT-4 as agents for trajectory interaction. The interaction process involves providing the model with task descriptions, examples, and feedback until the model achieves its goal or reaches its token limit. Section: COT rationales. We've made significant strides in improving the inferential abilities of large language models, LLMs, by using a method called chain of thought, COT. This method allows us to follow a step-by-step reasoning process. We use a reasoning framework called REACT, which first provides a COT explanation, or thought, before producing the final action. This means that every action taken within the interaction trajectories comes with a detailed explanation, allowing the model to learn the reasoning process that led to the action. For trajectories that were generated without thoughts, we use GPT-4 to add thoughts for consistency with the REACT prompting. When it comes to agent tasks that involve real-world scenarios, we face significant challenges. Even GPT-4 doesn't always meet our expectations for these tasks. To ensure the quality of our data, we carefully filter the interaction trajectories. Each interaction trajectory is given a reward, which allows us to automatically select high-quality trajectories based on the reward. We filter trajectories for all tasks, except for Mind2Web, based on a final reward of 1, indicating complete correctness. However, due to the difficulty of the Mind2Web task, we use a threshold of 2/3 to ensure we obtain a sufficient number of trajectories. We've found that models trained on filtered trajectories perform significantly better than those trained on unfiltered trajectories, emphasizing the importance of data quality over data quantity for agent tasks. We've developed a hybrid instruction tuning strategy to improve the agent capabilities of LLMs without compromising their general abilities. Recent studies suggest that training with diverse user prompts enhances model performance. Using the shared GPT dataset, we selectively extracted English language conversation, yielding 57,096 conversations with GPT 3.5 and 3,670 with GPT-4. Recognizing the superior quality of GPT-4 responses, we adopted a sampling ratio of 1:4 between GPT-4 and GPT 3.5 for better performance. We consider 2 datasets, the AgentInstruct dataset and the general dataset. The mixture ratio of these 2 datasets is defined as eta. Our goal is to find the best policy that minimizes the loss function. A larger eta should imply that the model is more inclined towards agent-specific capabilities rather than general capabilities. However, we observed that training solely on agent tasks performs worse on unseen tasks compared to mixed training. This suggests that general capabilities play a pivotal role in the generalization of agent abilities. To determine the best eta, we scanned from 0 to 1 in intervals of 0.1 on the 7B model and ultimately chose eta equals 0.2, which performed the best on held-out tasks for final training. For our base models, we choose the chat version of OpenLlama 2, given its better instruction following capabilities than base models and commendable performance on traditional NLP tasks. We standardize all data into a multi-turn chatbot-style format, allowing us to conveniently mix data from different sources. During fine-tuning, we only compute the loss on the model's output. We fine-tune models of sizes 7B, 13B, and 70B using Megatron LM. We use a learning rate of 5E5 for the 7B and 13B models, and 1E5 for the 70B model. We set the batch size at 64 with 4096 sequence length. We use AdamW Optimizer with a cosine learning scheduler with 2% warm-up steps. For efficient training, we employ tensor parallelism for the 7B and 13B models, and for the 70B model, we also utilize pipeline parallelism. Detailed hyperparameters during training can be found in the appendix. Section Summary. The chain of thought (COT) method enhances the reasoning capabilities of LLMs by providing step-by-step explanations before producing the final action. Trajectories generated without thoughts are supplemented with thoughts using GPT-4 for consistency. Filtering high-quality trajectories based on reward significantly improves model performance on real-world tasks. A hybrid instruction tuning strategy is introduced to enhance agent capabilities without compromising general abilities, and a mixture of agent-specific and general datasets is found to be optimal for training. The base models are fine-tuned using Megatron LM with specific hyperparameters. Section: Our approach. Our methodology. Explanation. In line with previous studies that have evaluated language learning models, LLM, as agents, we provide some definitions. LLM as an agent. TODO. Rewrite this paragraph from AgentBench. The assessment of LLM as an agent in an interactive environment can be thought of as a partially observable Markov decision process, POMDP. This process is defined by a state space, an action space, a transition function that maps states and actions to new states, a reward determination function, a task instruction space, and an observation space. In this scenario, we refer to the LLM agent as M. Interaction trajectory. The interaction trajectory of the LLM agent can be documented as a conversation history. Given that existing dialogue models usually involve two roles, the user and the model, U_I, signifies the user's input, while A_I represents the model's response. Each trajectory also has a final reward, typically indicating whether the task was completed successfully. Dataset construction. In this section, we explain the process of building the agent instruct dataset through 3 stages: instruction construction, trajectory interaction, and trajectory filtering. This process was fully automated using GPT 3.5 and GPT-4, making it easy to apply to new agent tasks. Agent Instruct includes 6 challenging tasks from AgentBench, which cover a broad range of real-world situations. Most open-source models struggle with these tasks. Instruction construction. Instructions for agent tasks are generally scarce due to the challenges in collecting real-world data. If a task has a training set, we use it directly for the next phase. For tasks without a training set, we use task derivation and self-instruct methods to create corresponding instructions. Task derivation. For agent tasks related to widely studied scenarios, we can create instructions from similar datasets. We used BIRD, a select-only database benchmark, to construct instructions for the database DB task. We ran 2 types of task derivation. First, we created a trajectory using the question and the reference SQL statement in each BIRD subtask. We then queried the database using the reference SQL statement to get the database output and used it as the agent's suitable answer. Finally, we asked GPT 3.5 to fill in the agent's thoughts based on the above information. This way, we generated correct trajectories directly from the BIRD dataset. However, since this synthesis process fixes the number of interaction turns at 2, we proposed another approach to increase diversity by constructing instructions instead of trajectories directly. We prompted GPT 3.5 with a question from BIRD, and collected its interaction trajectory with the database. After collecting trajectories, we executed the reference SQL statement from BIRD and compared its result to the one from GPT 3.5. We filtered out incorrect answers, collecting only trajectories that produced a correct answer. Self-instruct. For the operating system, OS, task, due to the difficulty in obtaining instructions that involve manipulating the OS in the terminal, we used the self-instruct method to construct the task. We first prompted GPT-4 to come up with some OS-related tasks along with explanations, a reference solution, and an evaluation script. Then, we prompted another GPT-4 instance, the solver, with the task and collected its trajectory. After the task was completed, we ran the reference solution and compared its result to the one from the solver GPT-4 using the evaluation script. We kept the trajectories where the reference solution and the solver solution gave the same answer. Since BIRD only contains select data, we constructed other types of database operations, insert, update, and delete, in a similar way. It's important to note that these two methods might risk test data leakage if GPT-4 outputs instructions identical to those in the test set, or if test tasks are constructed from the same dataset we derived from. To address this concern, we conducted a systematic analysis and found no evidence of data leakage. Details can be found in the appendix. Trajectory interaction. We used GPT-4 as agents for trajectory interaction. For the Mind2 web task, due to the large number of instructions and our budget constraints, we partially used ChatGPT for interaction. Following Agent Bench, we used a one-shot evaluation approach, mainly because of the strict requirements for output format in agent tasks. For each task, we provided a complete interaction process from the training set. Section Summary. In our approach, we evaluate the language model as an agent, LLM as agent, in an interactive setting using a partially observable Markov decision process, POMDP, framework. The interaction trajectory of the LLM agent is recorded as a conversation history, consisting of user inputs and model responses, with a final reward reflecting task completion. We construct the agent instruct dataset by automating the process using GPT 3.5 and GPT-4, covering 6 challenging tasks from Agent Bench. Section COT rationales. We've developed a method called Chain of Thought, COT, that significantly improves the reasoning abilities of language models. This method works by breaking down the reasoning process into steps. We use a framework called React to generate these steps, which we refer to as thoughts, before the model produces its final action. This means that every action is accompanied by a detailed explanation of the reasoning process that led to it. For tasks that don't already have these thoughts, we use a language model called GPT-4 to generate them. This ensures consistency with the React prompting method. When dealing with tasks that reflect real-world scenarios, we found that even GPT-4 can struggle. To ensure the quality of our data, we've implemented a rigorous filtering process for the interaction trajectories produced by the model. Each trajectory is assigned a reward value, which allows us to automatically select the highest quality trajectories. We filter trajectories in 3 different environments: ALF World, Webshop, and Knowledge Graph. We only select trajectories that have a final reward value of 1, which indicates complete correctness. For a more challenging task called Mind2 Web, we use a slightly lower threshold of 2/3 to ensure we have enough trajectories. Our dataset, as detailed in the table, contains 1,866 filtered trajectories. We've also developed a hybrid instruction tuning strategy. The goal of this strategy is to improve the model's abilities without compromising its general capabilities. To achieve this, we train the model using a mix of the agent instruct and general domain datasets. Recent studies have shown that training with diverse user prompts can improve model performance. We've used the shared GPT dataset to extract English language conversations. This has given us 57,096 conversations with GPT 3.5 and 3,670 with GPT-4. We've found that GPT-4 produces higher quality responses, so we've increased the amount of GPT-4 data we use by 5 times. We use a base model to represent the probability distribution of a response given an instruction and history. We consider 2 datasets, the agent dataset and the general dataset. Our goal is to find the best policy that minimizes the loss function. We've found that the model's performance first increases and then decreases as the weight given to agent-specific capabilities increases. This suggests that general capabilities are important for the generalization of agent abilities. We've chosen the chat version of the open-source Llama 2 as our base models. These models have better instruction following capabilities and perform well on traditional NLP tasks. We standardize all data into a multi-turn chatbot-style format. This allows us to mix data from different sources. During fine-tuning, we only compute the loss on the model's output. We fine-tune models of sizes 7B, 13B, and 70B using Megatron LM. We use a learning rate of 5E5 for the 7B and 13B models, and 1E5 for the 70B model. We set the batch size at 64 with a sequence length of 4096. We use the AdamW optimizer with a cosine learning scheduler with 2% warm-up steps. For efficient training, We use tensor parallelism for the 7B and 13B models, and pipeline parallelism for the 70B model. We've evaluated our model on 6 tasks from AgentBench, ALF World, WebShop, Mind2Web, and 3 others. For tasks that the model hasn't seen before, we've chosen SciWorld, MiniWab++, Web Arena, and 3 more. These tasks cover activities like science experiments and web interactions. This ensures a robust evaluation of our model on diverse, unseen agent tasks. Section Summary. The chain of thought, COT prompting method enhances language models' inferential capabilities by using step-by-step reasoning. The React reasoning framework generates detailed explanations, thoughts, before producing the final action, enabling the model to learn the reasoning process. Trajectories are filtered based on rewards to ensure data quality, and a hybrid instruction tuning strategy is employed to balance agent-specific and general capabilities during training. Section: General Tasks. We've put our model to the test using 4 tasks that are commonly used in this field. These tasks measure the model's knowledge capacity, MMLU, mathematical ability, GSM-8K, coding capability, human evil, and human preference, MT-bench. When we compared our model to others, we found that the commercial model that uses an API outperformed the open-source models in agent tasks. So, we chose to compare our model to GPT 3.5 and GPT 4, as they have comprehensive agent capabilities. We also evaluated the open-source Llama 22 chat version, which is known for its superior ability to follow instructions, a key requirement for agent tasks. To ensure a fair comparison, we had to adjust for differences in task difficulty. Some tasks are easier than others, which could skew the average scores. So, we normalized the scores for each task across all models, scaling them to an average of 1. Our model, AgentLM, showed significant improvements over the Llama 2 series in both held-in and held-out tasks, while maintaining performance on general tasks. The improvement was more noticeable in the held-in tasks, but the held-out tasks also showed an enhancement of up to 170%. This shows that our model has potential as a general agent. In fact, on several tasks, the 13B and 70B versions of AgentLM even outperformed GPT-4. For most of the held-in tasks, the performance of Llama 2 was nearly 0, indicating that it couldn't handle these tasks at all. However, AgentLM made far fewer basic errors, showing that our approach effectively enhances the agent capabilities of the model. We also conducted an error analysis, selecting 3 tasks from the held-in set and identifying common error types. The original Llama 2 made more basic mistakes like repetition or taking invalid actions. In contrast, GPT 3.5 and especially GPT 4 made fewer of these errors. However, AgentLM noticeably reduced these basic errors. We also looked at the effect of training the model exclusively on either agent or general instructions. Training only with agent data significantly improved the results on the held-in set. However, it struggled to generalize well across both agent and general tasks. When we included general data, AgentLM performed almost at its best for both held-in and held-out tasks. This highlights the importance of general instructions in model generalization. Interestingly, when considering the 7B, 13B scale, the improvement seen in held-out tasks from mixed training was nearly equivalent to training with just the general data. A significant leap in performance was only observed at the 70B scale. This suggests that achieving optimal generalization for agent tasks might require a specific model size. Section Summary. To evaluate the model's general capabilities, 4 tasks were selected: MMLU to assess knowledge capacity, GSM-8K for mathematical ability, human evil for coding capability, and MT-bench for human preference. The results showed that AgentLM outperformed Llama 2 in held-in and held-out tasks, with up to a 170% improvement in held-out tasks. AgentLM also demonstrated performance close to GPT-4 on general tasks, indicating its strong generalization capabilities. Error analysis revealed that AgentLM made fewer elementary errors compared to Llama 2, suggesting that our approach effectively activates the agent capabilities of the model. Additionally, training with both agent and general instructions significantly improved performance, especially at the 70B scale. Section: Effect of different tasks. Exploring the impact of various tasks. We delve into the mutual enhancements of different tasks by fine-tuning them individually using the Agent Instruct tool. For our in-depth analysis, we employ the Llama 7B chat model. Our findings, as illustrated in the figure, show that fine-tuning mainly benefits the task it is specifically applied to. While many tasks do contribute to the improvement of others, the Mind2 web task is an exception, offering minimal cross-task enhancement. This could be due to its unique single-round format, which is in stark contrast to the multi-round format of other tasks. The evolution of language learning models, LLMs, as agents. Before the emergence of LLMs, agent tasks were primarily dependent on reinforcement learning or encoder models like BERT. However, with the introduction of LLMs, the focus of research shifted towards developing LLM agents. A notable development in this area is React, which ingeniously integrated chain of thought, COT, reasoning with agent actions. Several studies have also applied language models to specific agent tasks, such as online shopping, web browsing, and exploring a household. Recently, with ChatGPT demonstrating advanced planning and reasoning skills, research initiatives like Rewu and RCI have started exploring prompting strategies and frameworks. These aim to enhance the efficiency of language models in agent tasks without the need for fine-tuning. The role of instruction tuning. Instruction tuning is a process that aims to align language models with human instructions, thereby producing outputs that are more in line with human preferences. The primary focus of instruction tuning is to train language models to follow human instructions across a variety of general tasks. For example, both Flan and T0 have shown the strong zero-shot generalization ability of language models that have been fine-tuned on multiple task datasets. Moreover, FLANV2 has investigated the performance of instruction tuning across various scales of models and datasets. Given the impressive alignment capability demonstrated by commercial LLMs, many recent studies propose methods to distill instruction tuning datasets from closed-source models. This is done to enhance the alignment of open-source models.